We don't do topic 5 of chapter 8, but I think it might be useful as a little background as we go on to topic 6, which we do cover. Now, in topic 5, we deal with what are called quadratic functions, graphs, and models. And the interesting thing is, in the previous section, we went over linear graphing, in which they were straight lines. But now, when we get to quadratic equations, or quadratic functions as we see here, and this is the standard form, and remember we can always put a y in substitution of our function symbol. If we were to graph this, we would get a parabola. So let's just take a look at some for a moment here. So there is your typical parabola, and if we had the equation y equals x squared, now notice it's sort of in slope-intercept form, but there is no y-intercept out here. It's just that your x is squared, and the slope is like a 1 here. That the point of intersection across the y-axis here is at 0. And that happens to be the lowest point of the parabola. That would be called the minimum. And that point right there is called the vertex. And this axis, the y-axis, is also an axis of symmetry. That is, if you fold the paper longitudinally, this line would go over that line. So a very typical parabola. And just a few more. As we look at this side view here, if y is equal to x squared, that would be this line. If we had y equals 1/2 x squared, notice what happens. The bell of the parabola starts spreading outwards. If this were a 2 and then x squared, this line would come in closer. And the last thing I want to show you is that if a, this first term, leading x squared, if that were a negative value, the parabola would open up to the bottom. Now we had said that what was in this position is the y-intercept. So here, if our equation was y equals x squared, that's the red line, and it would be plus 0, it would go through the origin. But if we stick a -4 in there, it drops the parabola down to the new y-intercept of a -4. And this is the last thing we'll go over. If we have our function where our value of x is in a parenthesis, -4, parenthesis, and that quantity is squared. Again, it's a parabola, but the negative being here, right there, actually shifts the parabola. Instead of where you might think negative is this way, its opposite side shifts it over to a +4. So this is called a horizontal shift, and one of the peculiarities of this formula. But some of this will be useful in our next lesson, which we'll start right now. Now in section 6, as we look at exponential and logarithmic functions, here's what we had seen in the previous lesson, where you had a function equals x squared. Now in exponential functions, we're going to have f of x equals a value of something, but the exponent is now the unknown. So b is our base raised to x, which is the exponent. Here, x is our base, and we're raising it to the second power. So here we can change values of our exponent and see what this looks like. And notice that in this definition of exponential functions, the base b is restricted to positive numbers, and b cannot equal 1. That's a restriction we have on b, because 1 to any power is 1. So it has to be a number greater than 1. So a few examples of exponential functions. We see we have fractional exponents up there, and even the square root of 3. Now, these are easy to figure if you're using a graphing calculator or any kind of calculator to put your info in. Now, to start to get a handle on this, and we're looking over here at the bottom where they'll summarize it, characteristics of graphs of the function of x is equal to a base raised to an x power. So a very common one, and the one they use to start us off with, is the function of x is equal to the x power. So what we're going to do is put various values for x, and then see what values for y, or f of x, that we get in this column. So 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is actually 2. Now 2 to the negative 1 power is just the reciprocal of what 2 is. 2 is 2 over 1, so the reciprocal of 2 over 1 is 1/2. Now we use 2 as an exponent. 2 to the second power is 4. And 2 to the negative 2 power is 1/4, just the reciprocal. Now we can put in there 3 too, just to get another point. 2 to the third power, that would be 2 times 2 times 2 is 8. And for a negative 3, that would be 1/8. So now we plot these points. So x is 0, y is 1, right there. X is 1, y is 2, right there. X is a negative 1, we go over negative 1, y is a half, right there. X is 2, we go over 2. 2 to the second, we said, was 4. So that's our point there. And a negative 2 is 1/4, so negative 2, 1/4. And then we go, x is 3, so 2 to the third power is 8. So we go third power up here, 8 is up there somewhere. So notice we get this nice typical curve. Now, as we go on in this direction, and we have negative powers, this goes on to infinity in this direction for our x values, negative infinity. But it never reaches and physically touches this x-axis. A line that is set up like this, where it gets closer and closer and closer to it, but never touches, is referred to as an asymptote, and this happens to be what direction? The horizontal direction. That's your horizontal asymptote of this graph. And this will be true for all values here. Now, if I had 3 to the x power, 4 to the x power, these lines would just keep coming in closer and closer to your y-axis, as we see in this case where it's 10 to the x power. Notice how close this line comes in. So again, another characteristic of what a graph of this type of function looks like. Now, how about if we have a fraction like 1/2? Well, let me set that one up. Okay, so I set it up. Again, we're going to use the same values for x. That is our exponent, and there 1/2 is our base. So, if our base is raised to the 0 power, anything to the 0 power is 1. And then 1/2 to the first power is 1/2. But how about if we put now there a -1? Well, just as we said before, it's now the reciprocal of this, so this is 2. So 1/2 to the second power is 1/2 times 1/2, which is 4. And to the -2 power, again, the reciprocal. And this is going to be 3. This is going to be 1/8. I said it correctly, but I put it in the wrong slot here. So, to the second power, this is the 1/4 here. And then the reciprocal is 4. This is to the 1/8, because it's going to be 1/2 times 1/2 times 1/2 gives you 1/8. And then if it's the -3, it's just the reciprocal of this, which is 8. So, notice what happens as we plot this one now. This was f of x equals 2 to the x power. Now this one is f of x equals 1/2 to the x power. And can you see that on this side, where it goes the whole number, the curve goes up nicely like this, and we plotted that one. And when we have the reciprocal of 2 as our base, which is 1/2, it's just the opposite side of this. So that is when we see a whole number raised to some power, the curve looks like this. If it's 1/2, it's just in a sense the reflection on the other side of this axis of symmetry. It still has our x-axis as the horizontal asymptote. And we did this one too. Now, if this were instead of 1/2, 1/4, the line would be in here closer, and if it was 1/10, it would be in closer still, but they always go through 1, because any base to the 0 power is 1. Alright, so lots of background on here, and now let's take a look at characteristics of graphs that are in this value. So in summary, it's always going to go through 1, and if they're whole numbers, will look like so. As they get larger numbers, they get closer to your y-axis, and if they're fractions, change color here, they're going to come from this side. and your x-axis is the horizontal asymptote. And if we wanted to do our domain, again, it goes off in x values to negative infinity, and this one will eventually go to positive infinity. And the range, again, it gets closer and closer to our 0 value, which is what our y value is here, but it never touches. So when it never touches, we use a parenthesis to indicate 0, and it's going to go up to positive infinity. Now, in an earlier lesson, we mentioned about Leonard Hard Euler, who was given the distinction of having the letter E named after him, and we said that E was approximately right here at 2.78, right there, about that. Anyway, if we were to graph that, again, that graph would look similar to what we've done. Everything goes through 1. But when we raised it to the first power, it wouldn't go through 2, but it would go up a higher just a little bit, 2.7. So the line would look like so. So instead of quite going through 2, it goes up through the value of E when this E is to the first power. And then it follows the basic shape of another. So there is its value right there. This is what E is. And you don't have to know the mechanics of it. Just know that it's like this. Now, most calculators, especially scientific calculators, have the letter E there. So you would just put E caret -2, and it would give you this approximation. E caret 1.3, and get this. E caret 4, and you would get this approximation. And there's the graph that I was telling you about before, where e to the first power so when e is 1, remember when it's 0, e to the 0 power, everything is 1. But now to the first power is about right there, which is the 2.7 that we told you about. Okay. Now, where does this all come in? Well, a real-life application of exponential functions occurs in the computation of compound interest. So, suppose that a principal of $P is invested at an annual rate of R in percent expressed as a decimal, compounded n times per year. If it's once a year, n would be 1. If it's biannual, it would be n would be 2. Quarterly would be 4. Monthly would be 12. Our n is compounded the number of times per year. Then the amount that you get after that time is A. And T is the number of years. So there's the formula. And again, something you'll need in your notes. And we now want to work it using a calculator. So the first thing we do is suppose that you have $1,000. It's invested at an annual rate of 2%, compounded quarterly. So that means it's going to be 4 times during the year. Find the total amount in the account after 10 years if no withdrawals are made. So what we're going to do here is very carefully start to substitute. We put the principal of 1,000 right there. Now there is a 1 in the formula. We put our rate as a decimal fraction, which is 2%, right there. And now is the quarterly, so we put the 4 there. And then in the exponent area, the number of times compounded is 4 per year, and it's for 10 years. So this is going to be a 40. So in your calculator, you're going to put, when you divide this, this becomes 0.005, add 1 to it, so this then becomes 1.005. Now the first thing you do is caret, raise that to the 40th power. That then gives you this, that you will multiply by 1,000. So after 10 years, when you multiply this, you have this new amount. You have made $220.79 in interest based on this deposit. And 2% is pretty good in these days. It used to be 5 and 6% and 7 and 8% in some cases. But now it's 1% or 0.5%. So this is pretty good. So that's what you might do if you are saving $1,000. Now, sometimes instead of compounding quarterly, you have a continuous compounding. When that occurs, this involves the number e that we spoke of earlier. Now, this is the special formula in which we use e, where something is compounded continuously. So basically, similar to what we've done, you put in your amount, and there's going to be $5,000. Now, you're going to then put in to your calculator the letter E, and you're going to raise that letter E to the rate, which we said is 2.5%. We have to put that in as a decimal, 0.025 times t, which is going to be for 4 years. And we would multiply this. That would be what our caret is that we put on E. And then once we get this, we multiply it by the 5,000. And we'll show you the work right here. Now again, 2.5% is not a great rate, but it's not too bad, especially in today's saving account rates and things. But there it is. And then when you do this multiplication, it comes out 0.9. So you put in your calculator the letter E, caret, and then you type in 0.1 and leave that in your calculator, and then just go times 5,000 and you get this. If you have your calculator, I'd like you to try this. I did it on mine and it worked out very well. Okay, so again, this is exponential growth, and if we had a graph, just to review this a little bit here, and we said our growth was like so, this was direct variation or linear growth. Now what we're saying is our growth is going to be exponential. So instead of a straight line, it curves up. And that's what we're seeing here. Now, as we continue in this section, we're going from exponential function, that is, we're raising things to an exponent. Our base here is 2. The exponent is 3. 2 to the third power is 8. We're now going to modify the pattern of this and convert it to what we call a logarithmic function, in which we say the log of base 2, the answer is 8, is equal to 3. Well, the log of base 2 that gives you an answer of 8 is 3. That is, if we convert this back into its other form, we say the base is 2, the exponent is 3, and that equals 8. So this is the exponential form, this is the logarithmic form, and that's what they're introducing here. So the exponential form is this, the logarithmic form is this. So where y is the exponent, b is our base, and x is our answer. So let's do a little bit of work and continue. So in this column we have the logarithmic equation, and in this column we have the equivalent exponential equation. So you need to be able to convert them back and forth. So let's use this one. Now this is read log base 3 of 81 equals 4. So our base is 3, our exponent is 4, and this equals 81. So here our base is 10, our exponent is 5, and it equals 100,000. Here our base is 1/2, our exponent is a negative 4, and it equals 16. Now here, this one's a little tricky, because our base is 10. Let's do that. Our base is 10. The exponent is to the 0 power. And our answer is 1. Anything to the 0 power is 1. Okay, and we can go through these, but you see them. We're going to let you do some. Now, we'll look at this graph in a moment here. As we look at the graph of these logarithmic functions, let's just do a little review of what we had exponential functions, where we had f of x equals 2 to the x power. The graph, we said, looked like so. Now, if we put this in logarithmic form, an interesting thing happens. It switches around and it looks like that. So we can see that this graph and this graph are reflections. We say that the logarithmic graph is the inverse, the reflection of this. And notice if they gave you one with a fraction, the fraction of this one would go this way. Well, the fraction of the log would go this way. And if it were, let's say, to the 10th here, which I saw there, notice how close this line now still goes through 1, but it goes up there closer. Just like we had this line when it went closer there. Okay, so these are the graphs of these, and it gives you some background. Now remember, you can use your notes based on what they're asking you. So they are giving you some more detail in regard to the inverse of these. Let me just sketch in. This is what the other one looked like here. This is what the logarithmic one looks like. And if they're fractions, it would be this way. And then 10 would be this way. Now notice when we had exponential functions, x was our horizontal asymptote. When we have logarithms and we're graphing them, the asymptote now is the y-axis, and that is called a vertical asymptote. Remember, the x-axis is horizontal, the y-axis is vertical. So we have a shift, well, vertical and horizontal, absolutely, of the asymptote when we do logarithms. Now here's a summary of graphs of logarithms, and particularly to note, the domain and range now change. Here the range will be from negative infinity to positive infinity, while the domain, because of our vertical asymptote, which is your y-axis, never quite reaches it, so we use a parenthesis, 0, and it will go to positive infinity. Now, the letter E is often used in logarithms, and we think of this as what we call the natural logarithm. And the symbol on your calculator for this is ln. And you might say, how come the letters are reversed for natural logarithm? Well, because originally the symbol was in Latin. And in Latin they put logrimus naturalis, natural logarithm. I don't know if my Latin is too good, but that's why the letters are reversed. So this is base E. So if we're having a function, as you recall in base E, then the log of base E would be very similar, except when it's coming up this way, it would be, well, there's the natural log right there. It would be about, for number 1, about right there at 2.7. And otherwise everything is very, very similar. Here is the summary of the graph. So it's going right there at 2.7. Again, it's the inverse of its exponential form that we said would go through 1 here, but then up through 7. And there is an axis of symmetry going right through there, where if you folded that along that axis of symmetry, these lines would overlap each other. And there is the natural log function that we're going to look at in more detail. And you need to be familiar with this one. This is not a 1, but the L. Well, natural log of E to the k power is equal actually to k. And the reason for it is that there is an unwritten E here, and E over E is 1, so therefore k equals k. So keep in mind that's the derivation of it, and just include it in your notes. We're going to be using that in an application to follow. And before we go on, there is another common logarithm. When it's base 10, we call that the common logarithm. When it's base e, we call that natural logarithms. And then any other base, they have to indicate it by the letter itself, or the number, I should say. All right, we're going to look at exponential models in which we are looking for doubling time. How long does it take your money to double? Okay, so we have a certain amount, P, is invested at an annual rate of 3.5% compounded continuously. So there's where letter E comes in. How long will it take for the amount to double? Well, we're going to say P, and there's our E, and it's to the rate times time is going to equal amount. I'm just putting this on the other side. So I'm then going to say I want my A to double. So that would be our original value of P. This amount now will be doubled, will be 2P. So I'm replacing the A with the 2P. So I still have an equation. I'm going to divide P out of this side by dividing by P. Divide P out of this side, and now I have, without the P's on both sides, I have this equals 2. I'm now going to convert this to a natural log. I'm saying the natural log of E, and this is going to be the natural log of 2. I'm allowed to do that. Now we had said in the previous slide that there was an E here, because this is what the natural log is, base E. When we have this arrangement of E and E, this side just becomes a 1, so we end up with this. The natural log of 2, which is what we have right there. Now, we want to solve for the letter T. So how do we do that? Well, we're going to divide both sides by this. And here's where your calculator comes in so handily. You're going to put natural log of 2, and then you hit the division sign in your calculator, and then you put this in. It's not a natural log, just a regular decimal, 0.035, and give that a try. Now, when you put that into your calculator, it's natural log 2. They'll have a parenthesis here. You have to close that parenthesis, then hit the division key, divide it by this, and you get then approximately 19.8. When I put it in, I forgot to put this parenthesis here, and it gave me some wild answer. But again, practice it. These are the steps that you would do. I just kind of switched them around. I like to have the T on the left here. Here they put it over at the left finally. Okay, let's go on. Well, here's another application where world population reached 6 billion in 1999 and has grown to almost 7 billion by 2010. Based on this model, what will the world's population be in 2020? Okay, so we're just going to, where the X is, put a 10 there. Now remember, we multiply this by 10 first, and it's E times that. Put this in parentheses, caret this in parentheses, and then you multiply that by this, and it gives you that. So I put this in my calculator and I did get this. Now for here, since you're multiplying it by 10, just take one of these zeros away in here. So it'll be 0.0754. And then multiply it by this and you get that. All right, now in example B, they're saying according to this model, the population will be this. But what will it be? When will it reach 8 billion people in what year? So we put the 8 there equals this, and then it would be 8 divided by this gives you that, and that equals that. Then we convert it to its logarithmic form. The natural log of this equals the natural log of that. Now notice when you have natural log of e, there is a sub e there. So this side then just becomes the exponent. So we're going to take the natural log of this, put that in your calculator, divide it now by this, and that will give you x. And x for 8 billion would be 18.9 years from 2010, which is about 2029. Okay, one more to go. And before we leave this page, this problem was over 2 pages, so you need to be sure you have some notes that shows you this protocol, or you can use your book if you get a similar problem. This is your model of how to do it. Now for half-life, which is a exponential form as well. This is something we've used in biology for a while. It's called carbon-14 dating. Now carbon-14 is a radioactive form of carbon that as the plant is alive, it takes in carbon to make organic chemicals from it. But once the plant dies, it no longer takes it in. But once it stops taking it in, there is a loss of this radioactivity that eventually follows this particular function. Now the A sub 0 is the initial time that you put something in, the initial amount of what you have originally. And then it's negative, so it's going to go down. So what is the half-life of carbon-14 if the initial sample contains 1 gram of this? How much will be left after 10,000 years? So again, you divide out the A sub O, and you're left with 1/2 equals this. And we convert it to the natural log. And when we put this natural log of 1/2 divided by this, you get x equals 5,700 years. So after 5,700 years, you would have 1/2 gram of radioactive carbon-14 left compared to what you had originally. That's what half-life is. So here they want us to evaluate this for a 1 there. I got a little carried away here. There's the half-life. Now in letter B, suppose you had 1 gram. How much of it would be left then after 10,000 years? Well, you know, over half of it's gone in 5,000 years. So if we put this these data into this equation, and then again solve it, it ends up as being 0.30. Putting that in our calculator. So of the 1 gram remaining, it would be about 1/10 of a gram remaining. Here, this is a recipe of determining time intervals. The concentration of a drug injected into the bloodstream decreases with time. So that's capital T in hours, at which the drug should be administered are given by, and this is the formula, and it's the natural log of this. So C sub 2 is the concentration of drug that is harmful, and C sub 1 is the concentration below which the drug is ineffective. So plugging your data into the formula given here, and we're going to go on to a little bit lower, we see that T comes out to be this. Now, it says round to the nearest hour to find when the drug should be administered. Well, you got T.75. If you waited and rounded that off to 3 hours, that would be below the effectiveness of the drug. So you have to round this to the 2 hours, and that's where they get this. Okay, this is a long lesson, and I'm not sure we're going to have time to do some things, but you will have your study plan and practice, and eventually we have one more lesson before our next test. And here's what it looks like.